This worksheet is going to deal with the different conformations of ethane, propane, and butane. Conformation is just referring to the different shapes that a molecule takes while it is rotating around its single bond. So it's just different shapes. Ethane, the 2-carbon hydrocarbon, so that's CH3CH3. Propane, the 3-carbon hydrocarbon, which is CH3CH2CH3. And then butane, the 4-carbon straight chain unbranched, CH3, CH2, CH2, CH3. So we're going to be starting by dealing with the ethane molecule. You're definitely going to want to use your model kit to build a model of ethane and sight down the carbon-carbon bond. So that means you want to hold your model in your hand so that the carbon atoms are stacked one directly on top of each other. So you're basically going to be looking at it from this perspective. You're not going to be looking at it where the carbon atoms are side by side. You want to view it so the carbon atoms are sitting right on top of each other, and then arrange those 6 hydrogen atoms so that they're all evenly spaced with respect to each other. If you do that correctly and you draw a Newman projection of what you see, you should have a carbon atom in the front, which we represent by a single dot, and a carbon atom behind it, which we represent as a circle. And then of course in real life, like when you're holding your model kit, they're basically exactly the same size, but we really exaggerate it in these drawings. And then you're going to have 3 hydrogen atoms on the front carbon, and they're all going to be 120 degrees apart from each other. And I'm choosing to draw them with this particular orientation, but when you draw this, like those hydrogen atoms could be anywhere in this drawing. Like, it really doesn't matter where they are. The key here is that they're all 120 degrees from each other, this angle right here. And then on your back carbon, you have another 3 hydrogen, and those hydrogens should also be 120 degrees from each other. And in addition to that, they should be, every hydrogen atom should be 60 degrees apart from each other. So you want to set this up so that all 6 of the hydrogen atoms, they each have this, 1/6 of a pie sort of a shape. The angle between these hydrogen atoms in these different projections is different conformations is referred to as the dihedral angle. It is technically defined as the relative position of 2 atoms that are separated by 2 atoms, which is super confusing, but it is looking at this particular angle right here, or, it could be this one, or it could be this one. It's talking about 2 atoms, so in this case, the 2 hydrogen atoms that are separated from each other by 2 atoms, that being the carbon atom and the other carbon atom right there. So the dihedral angle would not be the angle between 2 hydrogen atoms that are attached to the same carbon. It would be the angle between 2 hydrogen atoms that are attached to different carbons. And the dihedral angle for the Newman projection that we drew up here, that is 60 degrees. So all of these angles needs to be 60 degrees. Now we're going to rotate the carbon-carbon bond in our molecule. So you're actually going to take your model and you're going to rotate it until the dihedral angle is 0 degrees. So that means we're going to be rotating the carbon-carbon bond until this angle is now 0 degrees. So that means you're either going to move the hydrogens in the back or you're going to move the hydrogens in the front, doesn't matter which one you do, and you're going to twist it until that angle is 0 degrees. So there's my back carbon, there's my front carbon. I'm going to draw my hydrogens on the front carbon like this. And my hydrogens on the back carbon, they basically need to be in the exact same place because I need to have an angle of 0 degrees. It's kind of hard to draw that, like it's actually impossible to draw that. So we just kind of draw them as close together as possible. Oops, I'm drawing my lines incorrectly. We draw them just sort of as close as we can get them. And we all just know when we're drawing them really tight together like that, we all know that what we are actually referring to here is that this angle is actually 0 degrees, even though we can't literally draw it. So these 2 different Newman projections that we have drawn here, the Newman projection is this conformation or this representation right here. These 2 Newman projections represent different conformations of ethane. Remember, conformation just means shapes that these molecules take when they're rotating around a carbon-carbon single bond. And the 2 conformations are named staggered and eclipsed. So we have names for these 2 conformations, and the names are super logical. This one is what we refer to as staggered because the hydrogen atoms are staggered with respect to each other. And this one we call eclipsed because the hydrogen atoms are stacking or eclipsing right on top of each other. So now moving on, we want to think about the energy of these different conformations. We have this thing called steric hindrance. Steric hindrance is when we have two atoms or more than two atoms that are getting too close to each other. So steric hindrance is basically just crowding. When we have atoms that are getting kind of jammed too close together, we call that crowding or steric hindrance. And this is a bad situation for a molecule. Steric hindrance or crowding is unfavorable. It's high energy. The reason for this is because on the outer surface of all of our atoms, we have electrons. The outside of every atom is negatively charged with that electron cloud. So crowding causes our atoms to come too close together, brings the atoms close together. These atoms are not interested in bonding with each other, so as they're coming close together, they're not trying to bond with each other. And then we get that negative to negative interaction of the electron cloud, which is an unfavorable situation. So looking at our conformations or looking at your model, staggered versus eclipse, which one experiences the greatest amount of steric hindrance? We're going to label that as high energy and the other as low energy. So steric hindrance being a reference to crowding, what we're basically doing is trying to figure out of these two shapes, which one has the atoms in a more crowded configuration. And that's always going to be the eclipsed situation. The eclipsed is the one that has more steric hindrance, and therefore it is a high energy situation. Staggered, where the atoms are super spread out, that's a really low energy situation. All of the atoms are really happy. So high energy, unfavorable, low energy, favorable. Eclipsed, this is where we're experiencing steric hindrance, because the atoms are the hydrogen atoms specifically, are too close together. So now we're going to take this information and we're going to try to translate it to propane. That's our 3-carbon hydrocarbon. So I'm going to start just by drawing it in a Lewis structure. It's going to look like this. And I'm going to draw it's going to be like a Lewis / condensed, partially condensed structure. So here's my model of propane, and we're going to cite down the carbon 1, carbon 2 bond, which is this bond right here. The carbon in the front is represented by a single dot. That's going to be this guy right here. And the carbon in the back is represented by a circle. That's going to be my carbon number 2. And we're being asked to draw this in a staggered conformation. So on my carbon number 1, I'm going to have these 3 hydrogens. They're all going to be 120 degrees from each other. And again, it does not matter how you choose to orient these 3 hydrogens. You can have them angled in any way that you want. Like, it's really just your own personal preference. And then on my back carbon, I'm going to draw a hydrogen, and a methyl group. Because I'm drawing it in the staggered conformation, I want them in these positions right here so that I have 60-degree dihedral angles all around this. I need 2 of these spots to be hydrogen atoms and 1 of them to be a methyl, and it does not matter where I choose to put these different groups. So I'm choosing to put the methyl in this spot, but you could have put it here or here. It's just going to be, just sort of your perspective. So you could be drawing this in any way that you want. All that matters is that you have that 60-degree dihedral angle. Now, if this is the first time you've encountered this, or maybe the first time I've talked about it, writing this methyl group backwards, sometimes that throws students off. Like, they want to see it written like this, and now I'm writing it backwards. Why am I writing it this way? Kind of like the way that we draw condensed notation when we are writing substituents, like a methyl group in this case, coming off of a bond. We do tend to try to follow the order in which the atoms are actually bonded together. So if we were to expand this, if we were to draw it out like a Lewis structure, we would draw it like this. The carbon, which is actually attached to the rest of this Newman projection, which is why we choose to write it sort of in a backwards way, just again because it's more reflective of the true structure of the molecule. Okay, so next up we're going to rotate the carbon-1, carbon-2 bond, that's this bond right here, so that it represents the eclipsed conformation. And so when you do this rotation, it does not matter if you are moving the hydrogens in the back or if you're moving the ones that are in the front. Like, it literally doesn't make any difference at all. I'm going to keep my front bonds in the exact same spot, and I'm going to stack my carbon number 2 bonds behind it. And when I draw the carbon number 2, like, it doesn't matter if I've chosen to move the methyl group up here or if I've chosen to move the methyl group down there. It really doesn't make a difference. I'm going to put the methyl group up on top. All that matters in your drawing is that you're going to have 2 hydrogens eclipsed, 2 hydrogens eclipsed, and a hydrogen eclipsed with a methyl group. Which one is high, which one is low in terms of energy? Of course, due to steric hindrance, this is going to be our high energy, unhappy conformation. This is going to be our low energy, stable, happy conformation because the atoms are all spread out. And now we are moving on to butane. So butane, this is going to be our 4 carbon, and I'm going to begin by drawing a sort of like a partially condensed representation of butane. Because in this little exercise, I need to make that a little bit smaller. Actually, I'm going to put it down here. We're focusing on carbon 2, carbon 3. So what I'm going to do is expand carbon number 2, and I'm going to expand carbon number 3, and I'm leaving carbons number 1 and 4 condensed. So we want to draw this first of all build a model first of all and arrange it so that it's in a staggered conformation and draw it. And we're going to draw it in this spot. So we're focusing our Newman projection on carbon number 2 and carbon number 3. I'm going to be making carbon number 2 my front carbon, and carbon number 3 is my back carbon, and I'm going to set my Newman projection up to look like this. So this is going to be a staggered conformation. On my front carbon, on my carbon number 2, I have a hydrogen, and a methyl group, and I'm just going to draw those wherever I would like. So I'm going to do it like this. Hydrogen, and a methyl group. And then I'm going to do carbon number 3, which is the one in the back, and that one has the same thing, a hydrogen, and a methyl group. Now, when I draw these, I'm just going to put them kind of wherever I feel like putting them. You'll be, matching your model. There is more than one staggered conformation of butane. You can draw any one of them. So in this case, there is going to be, a totally different conformation where the methyl groups are, like maybe you have one here and you have the other one opposite. I've drawn it where they're kind of adjacent to each other. Don't worry, we're gonna draw all of them in these boxes right here. So if you didn't see this structure, you're eventually gonna see it. So what we're gonna do is rotate carbon number 2, the front carbon, 60 degrees clockwise. So we're being really specific in this case. We're gonna take the front carbon and we're gonna turn it 60 degrees clockwise. So it's all of the things on carbon are going to move, the front carbon are going to move like that. That is going to give us, since we're leaving the back carbon completely alone, I'm going to begin by drawing the carbon in the back and the things that are attached to it like that. And then here is my front carbon and my front carbon bond. I've got one of them right here. I've got one of them right here. And I've got one of them right here. And in my front carbon, I took that hydrogen on top and I moved it over here to like the 2 o'clock position. I took the hydrogen that was right here and I moved it into the down position. And then this methyl group, I've moved it up here to like the 10 o'clock position. So it's going to be a lot of letters smushed into there. Now we're just going to continue this, rotating the front carbon 60 degrees clockwise, and we're just going to keep going. So we're going to draw another Newman projection this time. Again, we have to keep doing, following the same pattern. We're going to take those front bonds and we're going to rotate them 60 degrees again. So this is going to bring us back to another staggered conformation. Going to set myself up for another staggered conformation. Again, no change to the back carbon, so I can start by copying that back carbon, not making any changes to that. And then for the front carbon, I'm going to start by taking this methyl group that I rotated 60 degrees. So the methyl group is now up here on top. And then the other two are the hydrogens. We're going to rotate again another front carbon, another 60 degrees clockwise. And since we'll start by drawing the back carbon, since we're never making any changes to that back carbon. Getting kind of tired of drawing these jammed up methyls. Now our front carbon, we rotated our front carbon 60 degrees, so everything is going to be eclipsed again. The methyl group was moved into this sort of 2 o'clock position, and the other spots have hydrogens on them. And we're going to go 2 more times. I'm going to start by drawing the back carbon, which has nothing moving at all. When you're doing these types of conformational analysis exercises, it's a good idea to pick either the front carbon or the back carbon. You just never touch it. Okay, so we're going to take our front carbon. We're going to go 60 degrees one more time. So that's going to put our methyl group in this sort of, what would this be like? Kind of like a 5 o'clock position. That's our methyl group, and the other 2 positions have hydrogens. And then we're going to do it one last time. Everything gets rotated one more time, 60 degrees, into one last eclipsed conformation. Start by drawing the carbon in the back. That carbon has not changed at all through this whole entire exercise. And we're drawing another eclipsed conformation. This time, the methyl group, which started right here, we rotated it 60 degrees, so the methyl group is now sticking down here. The other 2 spots have hydrogens in them. So we've got all of the different shapes on here. You, like depending on how you drew yours, you will see all of these shapes and you will see them all in the same order that I drew them, but you might not be starting in the same spot. So maybe you started with this shape. Maybe this was the first thing that you drew in this box. And then you would have drawn this one next, and then this one, and then this one, and then you would have drawn this one and this one. So you would have either started here, here, or here, but you would have drawn all of them in order. Of all 6 of these ones that we drew, 3 of them are eclipsed, and they all are high energy because they are eclipsed, but one of those 3 is more high energy than the other. So looking at our eclipsed conformations, which are here, here, and here, they're all high energy, but of these, one of them is absolutely the worst, and that's this one right here, because in this eclipsed conformation, we have methyls eclipsing methyls. In the other eclipsed conformations, our methyls are eclipsing with hydrogens, so it's not quite as bad. This one right here is the highest energy. I'm going to label that highest energy. It is out of all these conformations, it's the worst. This is just high. We're just going to call it high. It's not as high as the highest energy. And these 2 are exactly the same in terms of their energy because they have the exact same eclipsing situation. Even though the orientation, the position of these they're in a different spot, but we're still dealing with the exact same type of eclipsing. Then the other 3 remaining conformations are staggered, and they're all low energy, but like the previous one of those staggered conformations is even lower energy, even better than the others. So we're looking at this one versus this one versus this one, and one of these 3 is super low in energy, and that's the one that has the methyl groups as far apart from each other as possible, because that allows those methyl groups to really not experience any steric hindrance. These 2 are just low energy, not as low, and they are equal to each other in terms of energy because they both have the methyls that are 60 degrees apart from each other, so they have the exact same type of steric hindrance. The lowest energy conformation of butane is called anti, which is a prefix that we use to mean opposed. That's this guy right here. So the lowest energy conformation gets a special name, anti, and that comes from the relative position of those 2 methyl groups. They are anti or opposite or 180 degrees apart from each other. The other low energy conformations are called gauche. gauche, which is a very ugly sounding word. So these two guys right here, these are gauche, and gauche means awkward. I'm not sure exactly what it is about these structures that made somebody look at them and think, oh, these are awkward. They don't look particularly awkward to me, but that's the name that we give. So for a staggered conformation with the large substituents 180 degrees apart from each other, we call that anti. Staggered conformations where the large substituents are 60 degrees apart from each other, we call those gauche, the gauche conformation and the anti-conformation. And then what we're going to do next is look at, so this is the energy of the butane molecule as it rotates around that carbon-carbon bond, fluctuating high energy, low energy, high energy, super low energy, high, low, high. What we're going to do is take these letters A, B, C, D, E, F, and we're going to label them to the on the structures, the Newman projections that we drew over here. Or what we could do is copy these structures onto this graph. I think that's what I'm going to do. That's a lot of writing, so you might not want to do that yourself, but I have copy and paste, which makes it easier for me. And I'm going to erase some of the stuff that's on here, make it a little easier to look at. So what we're going to do is just sort of drag these different Newman projections to the spots that they belong on this graph. I am going to start with I'm going to choose to start with my lowest energy conformation. That's the anti-structure right here. So I'm going to take this structure and it belongs right here in this low energy spot. Where's a good place for it? We'll put it right there. And then it's important to, sort of keep these different structures in order, which means the next one that we should place would be the next one on our little diagram. So that's going to be this one. This is a relatively high energy structure. And then the next one that we have, we're going to go back to the beginning of the drawing. That's this guy right here. It is one of our low energy conformations, but not the lowest energy conformation. And then maintaining that order, here is our highest energy conformation, all the way up here at the top where those methyl groups are eclipsing each other, creating a really super high energy situation. And that structure is represented twice on this energy diagram. So I'm going to copy and paste it over to the other side. And then from that high energy conformation, we go back to a low but not lowest energy conformation. So that's this guy right here. And then last but not least, this guy right there. So you can do this exact same sort of conformational analysis with any molecule. It doesn't have to be done only with butane. But in general, in any molecule, your anti-structure, the one where you have the largest groups 180 degrees from each other, that's going to be your low energy. And your highest energy is the one where you have your largest groups eclipsing each other. That's going to be the worst. Your other staggered conformations are going to be low-ish in energy, and your other eclipsed conformations will be high-ish in energy.